Good morning, everybody. It is a great pleasure for me, on behalf of the Norwegian School of Sport Sciences, to welcome you all to this trial lecture in partial fulfillment of the requirements of the award of Doctor of Philosophy, PhD, in Sport Science. My name is Lars Tore Rongland. I am rector at NIH, and I will share the two sessions here today. In particular, I would like to welcome the members of the examination committee. Professor Anne Marte Bensgaard, Norwegian School of Sport Sciences. Associate Professor Keith Lowes, Washington University School of Medicine, USA. Professor Joseph Gallia, University of Birmingham, UK. Furthermore, I welcome the candidate, Christian Magelssen, who will now give the following lecture, The Neural Basis of Motor Skill Learning. Indeed, over to you, Christian.
Thank you for the introduction, and thanks to the committee for giving me this interesting talk for my trial lecture, which is the neural basis of motor skill learning. What are the dominant mechanisms underlying motor skill learning, and how does the central nervous system change as someone progresses from novice to an expert? And with that, let's get started. So our motor system is the oldest learning system that we have. It was developed long before we acquired other cognitive functions, like, for instance, language. Now, this learning system was originally designed to help us move in relation to objects and places in our environment, such as to help us harvest for food or to navigate around dangerous objects. Now, in our lifetime, we have decided to push this learning system to the most extreme, for instance, by learning to excel in elite sports, which requires many years of dedicated practice. And our society, they value skills when they see it, so they are willing to pay us lots of money if we, for instance, can hit a ball inside a hole from 150 meters away from the target with just a stick in our hands. Or they are willing to pay us lots of money if we can navigate down a slalom course in a reasonable time. So skills have an intrinsic value in our society. But what is motor skill, and what is motor skill learning? One approach to understand this is that the brain is a processing system that converts input from our sensory organs, such as vision, and convert that to some motor commands to give some output. Now, in this view, motor learning is a process of developing and refining motor commands to successfully achieve a task goal. Now, there are some important modules in this learning system, and one is the primary motor cortex, and that plays a crucial role in generating motor commands that initiate movements. And you can see the motor cortex here, and that converts signals to the spinal cord, and that causes movements. Then we have the basal ganglia and the cerebellum, and they are essential for refining these motor commands to optimize outcomes. And you can see the basal ganglia lies here, and the cerebellum lies here. Now, In recent years, or decades, I should say, neuroscience has begun to understand how these separate models help us learn skills. So neuroscience has begun to understand the neural basis underlying motor skill learning. And the way they have done this is that they have used, for instance, techniques like fMRI, EEG, MEG, and sometimes used transcranial magnetic stimulation. And in order to do this, they have used very simple tasks. For instance, this task, as you can see here, the learner is placed in front of a table, and the task is simply to move the cursor towards the target. Now, this is a very simple task in the very beginning. It's just reaching towards the target. But then on some trials, the scientist decides to rotate the cursor to the left or to the right so that the learner misses the target. And then the learner needs to adapt to this kind of rotation, and over multiple trials, the learner managed to do that. These tasks are great because it allows scientists to better dissect the individual components underlying motor skill learning. Now, from these kind of studies, neuroscience has come to the conclusion, or maybe come up with at least 3 different learning systems that seems to be important for learning motor skills. And these are unsupervised learning, reinforcement learning, and supervised learning. And this will be the basis of this presentation. I'm going to focus on these learning mechanisms. Now, as you can see, each of these learning mechanisms has their own neural substrate. So you can see that unsupervised learning involves the entire cerebral cortex, the mantle, whereas reinforcement learning involves the circuit between the basal ganglia and the cerebral cortex. And then you see that supervised learning involves the circuit between the cerebellum and the cortex. So these learning mechanisms will be the basis of my talk, but to help you understand, I'm going to look at what athletes need to learn in order to excel in sports, and then use these learning mechanisms to help to see how they can help learners achieve this learning. So what do novices need to learn to become experts? One is to learn to select optimal actions. So for instance, this skier that skates out of the start, he or she has to decide between, should I take strategy number A or should I take strategy number B? All right, so that's one component of skill learning. The second component is that once this decision has been made, it is also important to be able to execute those decisions. But that is not enough. It is also important to be able to adapt to environmental constraints, such as to different kinds of weather, different kinds of equipment, such as short skis and long skis. It's also important to be able to adapt to different course settings. So these are the main components of skill learning. And the rest of the talk will be about how these learning mechanisms can help us acquire those skills. The first I want to start with is reinforcement learning. So remember, learners must learn to select the good actions. That's one key element of skill learning. And reinforcement learning plays a particularly important role in learning to select appropriate actions. So here is an overview of reinforcement learning. And the core idea in reinforcement learning is that the learner learns through evaluation rather than direct instruction for a teacher. So this can be illustrated in the following way. You have a skier, and then the skier tries one action, And then there is, the learner needs to evaluate that action, see how good or bad that strategy or action was. I can describe this in a bit more detail. So with the following illustration. So let's say that we have 3 different strategies or action at our disposal. So we have action A, B, and C. Now, each of these actions, they have their own expected outcome. So if I, for instance, perform action number C, I expect that I'm going to give a particular result by following that action. And these expected outcomes allow us to compare the values. So we can compare each of these values, and then that allows us to choose the action with the best value. For instance, in this situation, we choose this color here. And then we can perform a trial, and that gives us an outcome. And then we can evaluate the outcome, such as how good was this strategy in terms of our expected outcome. And as you can see here, there is a difference between the current trial and our expected outcome, and this results in a reward prediction error. And then we need to update the value for that strategy, and then in order to better understand the strategy, so we can select the best strategy. Now, learning in this framework is driven by reward prediction errors, which are the differences between the actual and predicted rewards. These reward prediction errors can be better than expected, similar to expectation, or worse than expected. So in the case here, it is better than expected because the time was better than they expected. And what we should take away from this is that maybe we should choose this strategy in the future. It could also be similar to expectation, and that is when the current trial was actually similar to the previous or our expected value. And then our takeaway is that maybe choose this strategy in the future if that was a good strategy. It can also be worse than expected, and then the learning or take-home message is that maybe avoid this strategy in the future. The interesting thing is that there is some evidence that dopamine neurons in the midbrain seems to code this reward prediction error. So here we have a classic paper from Schultz. And what you see here is that we record from one single neuron in the dopamine cell. And then we have a trial with a monkey. And this is time. So this is before the monkey has learned anything. And the monkey is here presented with a stimuli, but the monkey doesn't know about what that means. And then sometime later, he's given a reward. And what you can see is that we have some activity in the neuron, but then we have lots of activity just after the reward has been presented. And that's because there's a reward prediction error. There is a better than expected reward. But once the monkey has learned this kind of mapping, then here the monkey has learned what the stimuli is, so when it's presented. And then when the reward is presented, there is no big activity, as you can see here. It's just neutral baseline activity. So that's here in this situation, there is no prediction error. But in this situation, the monkey expects to be given a reward. But then when the reward is expected to come, the activity from the dopamine neuron is depressed, and that's because it's also a reward prediction error. But as you can see, the activity from the dopamine cell has been moved to the predicted stimuli. So reward prediction errors are believed to drive synaptic plasticity in many areas to select better actions. So it has been shown to drive synaptic plasticity in the striatal neurons in the basal ganglia. It has been shown to drive synaptic plasticity in primary motor cortex. And this synaptic plasticity may be an important way in which the central nervous change as learner progress from a beginner to an expert. So this reward prediction error help us decide what to do in a given situation. All right. So now we have talked a lot about how it is important to select good actions, but that is really not the only thing that's important to be able to achieve elite accomplishment in sports. It is also important to adapt to different environmental constraints, such as different weather and snow conditions, different types of equipment, and different types of course setting. Now, now to understand this learning process, we need to move to another learning system, which is called supervised learning. In supervised learning, the environment provides an explicit desired outcome or target for each input. So let us say that we have a learner that has performed an output. Okay, it has taken an action, and then the environment gives some information about how good or bad that strategy was. Was it the correct decision to make, or was it not? So this output can be catered to what the target says should be the optimal solution in this scenario. And if there is a difference between what the athlete or learner did and what the target said the learner should do in this particular situation, that results in an error, and then that error needs to be incorporated in the learner so that they can change the action next time. Now, these targets, they can come from an external person, such as a teacher or a coach, but it can also come from an internal, so we have our own teacher embedded in our own body that helps us decide what to do. And I will try to explain or illustrate both. So supervised learning can be illustrated for decision-making in the following way. So let's say we have a learner that has decided to take action number B in this particular situation. But then the target or teacher in this situation says, hey, you did action number B in this particular situation, but you really should have done number E. And that results in an error, and that's it's a teaching signal to drive plasticity. It can also be illustrated for motor correction, such as, let's say that the skier has edged the skis with 30-degree angle in one turn, but then the coach says, hey, you need to actually edge your skis more. And this is also a difference, and that results in an error, and then that also needs to be taken into account, and the learner needs to update what to do in the next situation. Now, these can also be internally driven. So here there is no external teacher, but we have an internal teacher. So let's say we are this learner, and we have decided, okay, now I go for strategy number B in this particular situation. But the learner has skied on very short skis the last couple of weeks. So the learner actually expects that because these skis turn very rapidly, he expects to come out of this turn here. But then the learner is now on long skis, which it takes a long time to change direction, and instead the learner actually ends up here. And that is a prediction error, and the learner needs to update the next turns so that he can successfully achieve a good outcome in this race. And this is an example of internally driven supervised learning. So this is the typical supervised learning that is studied in the laboratory. and it's done in the following way. So here we see a learner, and the task is to reach towards the target. As you can see, that's a very simple task. Okay. But then the experimenter or researcher decides to rotate the target, as you can see here. So it's giving a rotation, and that results in an error, and the learner misses the target. But then, over multiple trials, the learner learns to adapt to this rotation and learn to compensate by moving the arm to the right to hit the target. Now, these kind of adaptations seem to depend critically on the cerebellum. So here we have some interesting results from a nice paper. And at the top, you see healthy controls. And at the bottom, you see cerebral ataxia patients. So here we have trial number from 0 to 120. And then on the y-axis, we have target error. So here, there is really no error. So that's when the learner just reached towards the target, and there is no rotation. But then on trial number 40, the scientist decides to rotate, and then that results in a big error. But then, as you can see, the healthy participants learn to adapt to this rotation over multiple trials, and they become pretty good at the end. But then the scientist decides to turn the rotation off, and again, that results in an error in the opposite direction, and then the learner needs to adapt to that as well. All right, so these adaptations seems to happen in the healthy controls, but that's not the case with the cerebral patients. So that's what you can see here. We have really no error when the participants reach towards the target with no rotation. When the rotation comes, you cannot see this kind of adaptation. So there's just a flat learning rate. And when the rotation is off, they are again hitting these targets. So we see some impaired adaptation in patients with cerebral ataxia compared to healthy controls. Now, we think that this adaptation involves training of a forward model. And this is a bit complicated, and it's a busy slide, but I will try to help to illustrate it. So let's say we are this learner, and we are in this position, and we want to reach the target. So that's the desired outcome. Now, in order to do this, we need to come up with some motor commands, and these motor commands results in an actual outcome, as you can see here. Now, the interesting thing is that these motor commands are sent to a forward model through an efferent copy of the motor commands. And what the forward model does is that it tries to predict the outcome. So in this particular situation, it tries to predict what is going to happen with these motor commands. And as you can see here, the learner predicts that the outcome will be the target. But the actual outcome could be a miss. And if there is a difference between the actual outcome and what the forward model predicts, that results in a sensory prediction error. And this sensory prediction error drives learning of the forward model, we think. And the interesting thing is that inside the cerebellum, we have something called the Purkinje cells. And what these Purkinje cells does is that they take some input, the motor commands and the sensory signals that arrives to the cerebellum, and then it makes some predictions. Now, a copy of these predictions is sent to the inferior olive, which acts as a teacher. So what is happening is that the inferior olive in the cerebellum takes these predictions and compare it with an observation. And if there is a difference between those two, That results in a sensory prediction error, and that is fed back to the Purkinje cells so that they can update on the next trial. So that is the main point from the supervised learning. Supervised learning is important for adaptation. This type of learning depends critically on the cerebellum. It is, for me, a bit unclear if experts are better at adaptation, but perhaps they are more sensitive to errors such that they adapt faster to changes in the environments. The last learning mechanism that I want to talk about is unsupervised learning. So in unsupervised learning, the goal is to find an appropriate modular architecture for a given task. And famously, the great scientist Kajal, who won the Nobel Prize in 1906, had this to say about how this could happen. Kajal predicted that learning new skills involves two plastic changes. One is to unmask pre-existing connections in the brain, so our brain has some already existing connections, and then we can exploit these connections. Once that has been done, then we can start to establish new connections. And I will try to illustrate how this can happen. So here we have a nice classic paper from Pascal and Leone in 1995. And here the task was for the participants to learn a piano-like task, like sequences on the piano, for 5 days. And then they used transcranial magnetic stimulation to probe the cortical changes of the motor cortex while the learners did this task, did this training. Now, I think this needs a bit more elaboration in order to understand, so to help you with this, I will try to illustrate what transcranial magnetic stimulation is. So here I made a drawing of TMS, as you can see here. The core idea is that you place a coil outside the brain of the participant, and then you can give it a short pulses of electrical current, and that creates a magnetic field according to Faraday's principles. And what this magnetic field is that does is that it can actually induce or stimulate neurons on the inside of the brain, and that can cause activity in the brain. And if you place it over the motor cortex, what you can actually do is that you can create some motor actions, like motor invoked potentials. So here you see an image of the illustration of the motor cortex, and you can see that it has a nice organization. So here you see that we have some, that the fingers are represented in some areas of the motor cortex. So what you can do is that you can move the coil to this area, and then you can try to stimulate those areas. And that's what the researcher in this study did. Sorry. So what you see here is that they used transcranial magnetic stimulation to understand how the changes in this motor cortex for the fingers, because the fingers are important for piano, how that changed over the 5 days. So in the trained hand, it began small, but then the representation for the fingers, they increased over the trials. That did not happen in the untrained hand, as you can see here, and that did not happen as much in the control subjects, which didn't learn this task. So that is one plastic change that could happen. Other studies, they have found other task-specific plasticity in other cortical areas. So here we have a nice review. I just took a sample of it. But you can see the task here, and then you see the different papers here. So in this Dragansky paper, the task was to juggle, and they did that for 3 months. And what you can see from the results is that we see some practice-induced expansion of the MT and V5. And this is an area that codes motion in the visual field. So This is an example of very task-specific plasticity, as you can see. But then that expansion decreased to baseline after 3 months with no practice. Similar, we found in Boyk, we had juggling 3 months, and then that also increased this visual area. So there is some evidence that there is some task-specific plasticity in cortical areas. So to summarize, we started with what the learner needs to do in order to become good in a sport. So athletes must learn to select good actions, execute actions well, and adapt to environmental constraints. And we have looked at 3 key learning mechanisms that seem essential for driving learning from beginner to expert. Reinforcement learning involving the basal ganglia seem important for learning to select good actions through reward prediction error. Supervised learning involving the cerebellum seems important for motor adaptation through sensory prediction error. And unsupervised learning involves the entire cortex, seems essential for neural plasticity to optimize motor performance. I never liked my students to walk out of a classroom with feeling that we have covered everything. So there's really more to the story. So these are changes that occur, but that I have not talked about. Strategy learning also seems to be an important mechanism in motor learning. Motor learning also appears to involve the basal ganglia in distinct ways. Initially, it engaged the associative circuit within the basal ganglia. As the skill becomes more refined, the process seems to shift towards the sensory motor regions of the basal ganglia, but there are, of course, many other, like plasticity, that happens. And that's the presentation for the day. Thank you.
Thank you very much to the candidate for the trial lecture. We have some minutes left, so it's time for the examination committee. If you have a question or two to the candidate related to the trial lecture, so please, Professor Galien. Yeah. This.
Thank you for a really interesting lecture. I thought you provided a really good overview of the neural mechanisms of motor learning, so well done. I suppose I just wanted to go into a little bit more detail on one of the points that you summarized at the end, in terms of the role of strategy and I suppose the frontal cortex. So, for example, would someone with a frontal lesion be able to learn these kind of tasks that you're talking about? So how important do you think strategy is within motor learning?
That's a good question. I think that's really an important element of learning. And I think that's I think that's a very important, and that's especially like the collaboration with the cerebellum. And like if you do an error in one particular trial, and then you have this activity in the frontal cortex, like coming up with a strategy to compensate for that. And I think that's very important, especially also, yeah, in athletes, yeah.
So I suppose, especially with skiing, do you think it's important that people can explicitly understand how they need to adapt their behavior, or do you think this is a very implicit process?
I think that's also a good question. In like in sports psychology, we have always thought that everything should be like implicitly learned, and I'm like, I don't think that's maybe a good way to approach it. I think it's like everything is a contribution between explicit learning and also like implicit learning. And the explicit learning is very important to come up with like some explicit strategies how to do it in a particular situation. And I don't think that that will be like compress performance in some kind of way, even though like there is some evidence to suggest that. But yeah.
So one final question is, so this made me think about the nature versus nurture debate, in that you kind of explain that people can learn all of these things, but if I imagine that if I skied for 5 or 10 years, I'd still be pretty bad at it. And so what do you think, how much can people learn versus people have to have an innate ability to become an elite athlete?
Oh, that's a very broad question, but I think I think everything, like, of course there is some genetics involved, and so we have some innate abilities, but that is not enough at all. What you need to do is that you have some specific type of training. And what you can see is, that's a good example. If you look at the best skiers in the world, they typically come from the same type of environment. So they seem to have done some special types of training in that environment. And that's just an example that, yeah, like practice plays a very important role for learning skills.
Okay, so one thing, and I think we'll come back to this in terms of when we go through your thesis, is you've set out these kind of independent learning mechanisms. How independent do you think they are? So there's, for example, there's lots of evidence that you see reward signals in the cerebellum, and you've also highlighted that there's kind of dopamine in the primotor cortex. So how much do you think they interact, and how important do you think it is to look at these in an independent way when they probably interact a lot, especially with complex tasks like skiing?
Yeah, that's a very tricky question as well. I think they all cooperate and collaborate or compete, but they are always involved. Like, you cannot like separate them out, tease them out. Okay, now take cerebellum, now do your thing, and then we leave the other areas away. I think all is involved in producing motor commands. So I don't think you can like distinguish and separate them out.
Do you think it's important to look at them independently still?
No, not really. I think it's important to try to understand. If you cannot isolate or dissect the individual components of learning, I think it's still of value to like try to understand how you can weight the contribution of the individual components, and that's also an important way to do like research. So that's what I done in my thesis, is that I know there is like supervised learning occurring in the skiing hall. I know there's some other learning mechanism involved, but my goal was really to try to, can we give weight to more like reinforcement learning, for instance, and do more of that? Can that help us improve performance and learning? Yeah.
Thank you very much so far. It will be possible to discuss these issues later today. So I thank the candidate again for the trial lecture. I invite everybody to return to this auditorium at 11:30. Provided that the examination committee finds the trial lecture acceptable, the candidate will then defend his thesis, Improving Teaching and Movement Strategies for Skill Learning and Performance in Skilled and Elite Alpine Ski Racers. Thank you all.